going to continue the stuff we started last week. I'm going to start by talking about causality. Remember last week we saw the formal model? So remember how it works? You have comp events and delivery events. The delivery events brings the message to the destination node. So the comp event can send the message and then it disappears, it's in the network. And the delivery event makes it appear again, back on the destination, okay? And then we had causality. Events can be connected somehow, sometimes, when one event depends on the other, or not connected. That's the most important thing, because if you reorder the events and you respect causality, the result will be exactly the same. It doesn't actually matter exactly when the event is executing. Okay? If you respect causality, it will be exactly the same. And that's very important. So causality is a big thing. And I will first talk about how you determine causality. This is with something called a logical clock. And then I will go on. I'll talk about complexity. And I'll give you a paradox. This is kind of an exercise for you. Okay? But before I continue, a few seconds of respect for the Ukrainians who are fighting for their freedom and for Europe's freedom. Okay, so today I want to first talk about logical clocks. Okay, and there's two of them, Lamport clock and vector clock. Then we'll talk about complexity and then the implementation, how you implement the algorithms, and I'm going to introduce a really nice pseudocode, which has a very strange name, event-based component model. This is the best programming language for building distributed systems, by far. However, it doesn't exist. Okay, so that's kind of a pain, but for the course, it's really the best. It lets you write the distributed algorithms really simply, because it's doing exactly the right concepts. So why is our existing systems not implementing this? A very good question, okay? The closest one is airline, and even airline does not do everything this model does. So this is by far the best. So maybe one of you guys will invent a new language which is based on this. But in the meantime, this is just a pseudocode. And then I'll talk about specification. So implementation is the code, but specification is what you're implementing. And there's the properties. So the two properties are safety and liveness. So these are all properties are either safety or liveness. There's also the interface, the API. And finally, the model is what it runs on top of. So the failure, what kind of failures, and the synchrony, is it asynchronous or synchronous or partially synchronous, okay? So first, the logical clocks. The first clock I want to present is called the Lamport clock. So Lamport is Leslie Lamport, is the great founder of the discipline of distributed algorithms. Each process has a logical clock. So a logical clock is not giving you the time in seconds or anything like that. It's giving you the time as an integer. It's counting, okay? And it's counting events, comp and delivery events. And the Lamport clock has one integer for each node, okay? Which I will call t. So each node has a variable t. And while the system is running, the t is updated all the time. And each time you send a message, you piggyback t and also the process ID on the message. And when you receive a message, so the delivery, you update the t. So you have the local t and the t on the message. You take the max plus 1, okay? So you see you're actually always making new values. And when you do a pure comp event, which is not a delivery, you actually just increment t, okay? So that's the Lamport clock, and I'll show you an example of it. But you can already see some very interesting properties. Okay? If A happens before B, then T of A is the Lamport clock. So that's a number, an integer. Then T of A is less than T of B. So if I have two events that are causally related, I can tell which one is before by comparing the Lamport clock. So the Lamport clock tells me something about causality. Okay? But you can do more tricks with the Lamport clock. It's actually a very interesting thing. For example, if I have lots of events and I want to order them somehow, I have an event here, an event there, I somehow want to see which one is first. Well, I can use the Lamport clock to define a total order. So each event will have a pair, which is the timestamp of the event and the process ID. Okay? But when I want to compare the two events, well, the Lamport clock could be less, but if the Lamport clock is equal, I can compare the process ID. So the process ID is like a tie break. Okay? So 5, P5 will be less than 7, P2, because 5 is less than 7. 4, P2 is less than 4, P3, because 2 is less than 3. So you can make total order among events. It's actually very nice. If I want to do distributed database, and I have an update, and I send updates to both of them, and I want to do the updates in the same order, I can use this to define the same order. Okay? But let me show, first I'll give you an actual example. This is all very theoretical. So here's an example of a Lamport clock. So this is the time-space diagram. Remember, time goes from left to right. This is the events on each process. There's 3 nodes here, and the red zeros are the values of the Lamport clock. Okay? So in the beginning, it's 0, 0, 0. But when I do one event, when I do one comp event here, this Lamport clock is incremented, so it's 1 now. 1, the 2 others are still 0. And each time I do an event, I will increment the Lamport clock. So after the second comp event, it's 2. Then there's a third one. But this one is then also going to send a message, but it will also increment. This is also a comp event. The next event in time is here, is on P3. So what's going to happen? What value am I going to set here? 1, huh?
1.
0 plus 1. It doesn't, P3 has no idea what's happening in P1, huh? Okay, so this will give us 1. And now we will have this one. Remember, it's the max of the local value plus the 1 on the message plus 1. So what value is coming here? 4, huh? Right? So it's 4. Okay. And then the top one is also 4. So you can see the Lamport clock is the same for these two. So it doesn't really tell me if the events are causally related. Huh? You see these are the same, but in fact these are 2 concurrent events. Huh? So then I keep going, and I get 5, and I get 6. Okay? So the 6 here is the max of the 5 and the 1 plus 1. Huh? So you see the Lamport clock is always incrementing, and you can kind of give it a meaning. If I have a Lamport clock, it's the number, it's the maximum length of a chain of causally connected events. So the 6 means that there's these 5 guys before it, okay? The 4 means there's 3 before it. So you can kind of see it like that. And it's a very simple thing. Any algorithm, you can do it. But of course, it's a problem. It's not giving you so much information. When I have this one and this one, 1 and 4, but I still don't know which one is, if they're causally related or not. Now this one and this one are independent. So 1 is less than 4, but that doesn't mean anything, okay, because they're actually concurrent. So the Lamport clock is not actually giving me so much information. It's not smart enough. So the smart clock is called the vector clock. And you need more information. If you really want to determine causality, one number per process is not enough. You need more. And what you need is a vector. Each process has a vector of size n. So n is the number of processes. So it's a local variable, like the t, but it's not one number, it's a vector. And it starts out being 0. And again, you piggyback, just like for the Lamport clock. Otherwise, it's almost the same as the Lamport clock. Every message, you piggyback the vector. When you do a local event, you increment the vector, but only the index of where you are. See, the vector tells you for each process how many causal events are there before you. So if you do on node P, you do one comp event, you only increment index P, okay? And if you have a local, a message come in, of course, again, you take the max, okay? Before incrementing, just like for the Lamport clock, okay? But vector clocks are actually very smart. And you can compare them, and they will tell you everything about causality. So here's how you compare. So I'm comparing two vectors. So one vector, for example here, one vector is less than another vector, or less than or equal, okay? If each element is less than or equal, and it's less than, if it's less than or equal, and if it's different, if there exists an I where it's not the same. So the easiest to define is less than or equal. It's less than or equal for all elements. And if it's strictly less than, that means it's less than or equal and it's not the same. Okay? But it's possible that we don't, this is not always true. So VP and VQ are concurrent if VP is not less than VQ and VQ is not less than VP. So it's not comparing numbers, Not, if VP is not less than VQ, that does not mean that VP is greater than or equal to VQ. This is a partial order, and it tells you everything about causality. It'll even tell you when the elements are concurrent. So the vector clocks guarantee in both directions. So if VA is less than VB, according to that definition, then we know that A is causally before B. That A and B are causally dependent, and B is later. And if A is causally before B, then the vector clock is less than VB. VA is less than VB. And if neither of those is true, then A and B are concurrent. So the vector clock is telling you a lot more than the Lamport clock. It's telling you also when it's concurrent. So let me show you an example now. So this is like before, but here now we have vector clocks. So we have three vectors, 0, 0, 0, 3 times. We do first on P1, and then it turns into 1, 0, 0, because P1, we have an event happening on the first node, so we only increment the first one. See, and then the second one, and here the third one. And now, so what we do one more, and then we'll do P3. Oops. Okay. Why is it going forward? Is there something set, value set here? Okay, I hope it doesn't go forward. So what happens here? Here we have one event. So this turns into 1, 0, 0, but we have also 3, 0, 0. So basically we have to take the max of these two and then add 1. But 1 in the second element, because we're in P2. So what vector comes here then? So the max is every element max. Plus incrementing the second one, and that gives what? It gives 310. Well, so the next vector element would be 310. And then we have 400. And then here we have what? 320, because we're incrementing the second one. Okay, and the final one is what? So the max is 321, right?
Yeah.
And then we have what here?
322.
322. Okay, so you see it's not so hard. Huh? So you can add it to any algorithm, huh? And you can give some intuition to it. What this number means is that at node 3, I know there are 3 causally previous events on node 1, 2 causally previous events on node 2, and 2 causally previous events on node 3. Okay? The 2 ones on node 3 are these 2, the 2 ones on node 2 are these 2, and there's 3 on node 1. Okay? Notice here we have 001, even though these 3 events happened before. You see that? But it's still 001. Why is it 001? Well, it's what you know at P. So P3 is not omniscient. P3 only knows its own view of the world. And so P3 does not know that there are these 3 guys. According to P3, I only know of 0 causal events from P1. I know of 0 causally earlier events from P2. I now know of 1 from P3. You see? So it's the knowledge of each node that you're giving here. Okay? So that's nice, right? There is a small problem. Is scalability. You can actually prove that if you want all the information about causality, you need vectors of size n. So if I have 100 nodes, I need a vector of size 100. And each time I send a message, I have to send a message size 100. Question?
It was about you have to add this on the message and then it's not practical.
Yeah, so there's a scalability issue here. So if you have, the bigger the system gets, well, that vector has to be piggybacked on every single message. So this is a problem, okay? So really big distributed systems, it's a research question. Computing causality, it's really not practical for really large systems like Facebook, which means that Facebook does kind of an approximation, and sometimes it makes a mistake, okay? Maybe you haven't seen it, but it happens when there's lots of people in a discussion. Sometimes you get the answer to a question before the question, okay, which is kind of weird, but it's not causal. Because doing this for very large systems is not scalable, it's not practical. But you can't do it for less. Because you need all this information, okay? You need n vectors. You can prove that. So that's a problem. So we'll have to survive somehow with that problem, okay? So here's a question for you guys to see whether you have mathematical minds. So you know mathematically what is a partial order and a total order, huh? So if I have a set and there's an order, total order means every 2 elements are ordered. Whereas if some pairs are not ordered in the order, then it's a partial order. Okay? So, the happens before relation on events. Is it partially ordered or totally ordered? You tell me. Are all events ordered causally or not? What did I hear there? I heard a yes. Ooh, that's very dangerous. So it's not, you have concurrent events, right? So it's a partial order. What about the less than. So this is the arithmetic comparison of Lamport logical clocks. I'm comparing two Lamport logical clock values. Is that a total order or a partial order? You tell me. Mathematically. Any mathematical minds in the audience? Sorry? It's a total order because I'm comparing natural numbers, right? They are ordered. It may not have any relation to reality, but they are ordered, okay? And finally, the less than relation on vector timestamps, the way I defined it. Partial or total order? You tell me. Oh. Well, if I have two concurrent events, what do the vector timestamps say? What if I have this? 0, 1, 0, and 0, 1, 0, 0, and 0, 1, 0. Which one is less than the other?
They are equal. No.
They're not equal, but they are not comparable. So these two events are concurrent. So the less than relation on vector timestamps is a partial order. Okay? See that? Easy, yeah? So summarizing, okay, the Lamport and the vector clock. So those are the two ways of doing logical clocks. Huh? So the Lamport clock, the easy one, if A happens before B, then the Lamport clock is less. Okay? But that's all you know. But the vector clock tells you more. If A happens before B, then it's less. But if it's less, then A happens before V. That's very interesting, eh? It tells you whether or not the two events are actually causally connected. So, intuitively, so I have these two properties, in two directions. Which of these two is more useful? What do you think, in practice? Which of these is more useful? Just your intuition. What do you think?
The second one.
The second one, huh? Why is it more useful?
Because it gives us information we don't have.
Absolutely, it gives you a very strong information. Huh? It tells you whether or not the two events are actually causally related. So whether or not there's a chain going from one to the other, that's a very useful and strong information. Huh? So clearly the 2 is the more useful one, but the Lamport clock is not giving you that. Okay. Okay. So the extra information, yeah, so that's easier, that the vector clocks give is whether or not the events are causally related. So that's very useful, important. Huh? So if the number of nodes is small, then we can do vector clocks. But if you have large number of nodes, like 100 or 1,000, then the vector clock is kind of not scalable, huh? Because every single message you have to send the vector. So what do we do? Well, there's lots of ways of finessing this problem. For example, maybe we're not interested in all events, but only substantive events. Maybe we're doing broadcast algorithm, and we have broadcast operation. But each broadcast operation causes a big, complicated algorithm to run, so there's many events running a broadcast. Huh? But I'm not interested in those little events. I'm only interested in the actual broadcast events. So the number of interesting events is much smaller, and this means that I only have to keep track of the causality between the interesting events. So maybe that will make it more efficient, huh? Which is the case. Huh? So summarizing causality, the total order of executions of the events is not important. Two executions can yield the same result if the causality is the same. So it's only the causality is important. Okay? So we have defined it, the order of events on the same process, the order of send and receive, and then there's transitivity. This guy is what makes it non-trivial and hard property. This transitivity this turns it from order n to order n squared thing, because there's lots of transitivity. So transitivity means there's some path in the system of causality. There exists a path, and your system can be very big. Okay? We have talked about similar executions. So these are executions that preserve causality. The permutation. So the total order of events is different, but the causality is the same. And so they're actually doing the same thing. They're computing the same result, and we call it a computation. Okay? And the vector timestamp lets you determine causality exactly and precisely. And you need a vector of size n, unfortunately. If you want to do it with smaller, then you have to give up something. Okay. Okay, so that's all I want to say right now, but we're going to come back to causality. Now I want to talk about complexity. And I want to give you a kind of paradox. It's not really a paradox, but it's a subtlety, and it's important to understand. And when you understand that subtlety, you will really understand complexity. Okay, so now we want to determine how efficient our system is, and we're going to talk about the number of messages. That's one way, yeah? You run an algorithm and lots of messages are traveling. So how many? So that's one way of doing complexity. The other one is the time. How long does it take? But it's logical time, okay? And we're going to count messages and time until the algorithm terminates, okay? And when all the states are terminated and there's no messages in the network, that's important. The network is empty. So if there's one message still floating around in the network, it's not terminated, okay? So message complexity is defined as follows. So we count all the messages that the algorithm sends. And the message complexity is the maximum number of messages until termination for all admissible executions. So it's kind of a worst case, huh? This is a worst case complexity. All admissible. So what's an admissible execution? Do you remember? Admissible is a concept you know already. It's basically the same as fairness in a concurrent system. It means everybody is allowed to go forward. Nobody is starving, okay? Which means all messages are eventually delivered, and all processes go forward, and the executions are infinitely long, okay? Because we have an asynchronous model, we don't know how long. So we have to allow a message to stay in there for as long as it wants, okay? So this is the definition of admissible, okay? So for all the admissible executions, okay, we have to count how many messages, okay? And we take the one the most. So these two admissible executions, they might not be causally preserving or anything, huh? They might actually be very different, huh? The only thing is now fairness, huh? Okay? So this is not the same as similar executions, huh? It's a totally different thing, yeah? Admissible executions can be very different, okay? Okay, the time complexity. Now this is a little bit harder because we're not actually measuring time with a watch. It's not physical time. It's logical time, okay? So how do we measure logical time? Well, we're going to give it a kind of intuitive definition. There's message delay and computation events. We're going to assume that computation events are 0 because they're usually very, very small in terms of the time, the physical time they take, and the message delay will be 1 unit. Okay? We'll assume that when the message is sent and delivered, we count that as it's like 1 delay step. Okay? Okay, so we don't really care how long the message is actually sitting there. It's between the send and the receive, we consider that 1, or at most 1. It could be 0 or 1. Okay? And now we can define a timed execution. So we're actually taking an execution and adding information so we can compute the time. So we have a time attached to every comp event. The first event is time 0. The time is only increasing locally. Okay? And multiple comp events will not increase the time. Okay? 0 time limits. But we can have a comp which is sending and a comp which is consuming. So after the deliverer, that is actually, there's a message delay in there. So that one will be 0 or 1. Okay? Reasonable. And then again, the time complexity is the maximum for all admissible time. So this is actually a subtle thing. We're not just looking at one execution. We're running the algorithm. The complexity is kind of a property of the algorithm. It's not a property of one particular execution. Time complexity is a property of the actual algorithm. So it's defined for all admissible timed executions. Okay? So we don't really care. If there's one slow execution in the bunch here, then the time execution is going to be very big. Okay? Okay? So that's kind of very intuitive. If I have something like this, and there's a message sent, like, if it's like this, here I have 1, 2, 3, 4. Delay is 4. See that? So it's kind of like how many, if you go from the start to the end, how many message send receives are in there. That's the time complexity. Yeah? Okay? Now, you might ask yourself, why do I say at most here? Why don't messages just always take 1 unit? No, they don't. They can be 0 or 1. Why? That's a weird thing. Why don't I just say it's 1? Why not assume every message takes exactly 1 time unit? Intuitively, that seems reasonable, right? But now we have now it gets subtle because, remember, we're defining a model here. And it turns out, if we make it exactly 1, then we're not modeling reality. That's kind of strange, It will not give us reasonable numbers if we assume that the delay is exactly 1. So there's something interesting going on here for the message delay. So let me go a little and dig into it. So there's 2 possibilities for the message delay. It's either at most 1, so it means 0 or 1, or it's always exactly equal to 1. So those are 2 ways of defining the time complexity. It's the maximum time for all admissible executions, and then the message is either at most or exactly equal to 1 delay. So there's 2 ways to define that. How do they compare? So this is a very interesting question. How do they compare? In order to make this more concrete, I'm going to give you an algorithm now. Okay? I'm going to present to you a simple broadcast algorithm in a distributed system, and we're going to calculate this time complexity. And hopefully that will help you understand what's going on. So we have a network here, okay, and we have a bunch of nodes. So I think I take some kind of a network. The nodes which have neighbors. Something like that. One of the nodes is the source. Okay, so that's the source. So let me call this one the source. Could be anyone, huh? Let me just say this one. And I'm going to define now an algorithm that will broadcast to everybody. Will broadcast. Okay. Every node has a local variable called the parent. Okay? And n is a constant, which is the total number of nodes. Okay? And every node has a fixed set of neighbors that it knows, and that it can send and receive messages to. Okay, that's reasonable, huh? So here's the algorithm. So I have two rules here. This is the code I run for the source node, and this is the code I'm running on all the other nodes. And there's two kinds of messages that are sent, A and B. So I have A in little n little brackets and B. So when I do a broadcast, I'm always broadcasting starting from the source. Okay? So I send A to all the neighbors, and then I wait. So basically here I'm going to send an A. Okay, I'm going to send another A here. And then this stuff is going to happen, and eventually B's are going to come back. And I wait until I've received n minus 1 B's. So that is kind of telling me that the broadcast is finished. Everybody has received. Okay? So I can acknowledge it. So how is this implemented? Well, it depends on the code from the other nodes. So this is the code. So there's two conditions. The nodes can either receive A or receive B. When a node receives A from P, from one of its neighbors called P, then it executes the following code. It has a local variable, parent. If parent is still null, that's the initial value, then A is the first A that I got. It's the first one, okay? And then I'm telling that the local parent is equal to P. Which means that the first node that it sends me an A, that node will be my parent. Okay? And I forward A, I send A then to all neighbors except parent, and I send B back through the parent. Okay? So you see I'm receiving an A, I send A's to all my neighbors, and I send B back through the parent. That's the code for A. For B, it's very simple. When I receive B, I just forward it back up. So all the B's are going to be floating back up through the parents. You can see that the parents are actually going to make a tree. Okay? This is called a span tree. This network, which might have cycles and so on. So let me say, so this node, I will make the parent of this node will be this node. Okay, the parent then will be this one, and so on. Here also the parent of this one, but this node here, there's two possibilities. Either it gets the A from the left, or it gets the A from the right. Okay, so if it gets the A from the left, then the left one will be the parent, okay, and not the right one. So assume it gets it from the left, okay. Then the left one, so the first A, okay, notice if parent is different from null, it does nothing, okay? So it's only going to do one thing. It now receives second A here, but the second A will do nothing, okay? So basically the tree will be built according to the first A that has been received, okay? So let's look at this node now, this one. Now there's two possibilities. Either it gets A here, or it gets A through this detour. So it might get the A like this, huh? If this is faster than this, okay? And then we have this, we have this. So the red drawing that I made is a tree. So it's a structure with no cycles, which is superimposed on the original network. And the tree is built according to how fast the messages are sent. Okay? Okay, so this is a nice algorithm, right? Now the question for you is, what's the time complexity of this algorithm? And there's two possibilities. What is the time complexity if every message takes at most 1 time unit? Or what is the time complexity if all the messages take exactly 1 time unit? And you can see there's a difference, huh? For example, if I'm here, if the messages take exactly 1 unit, then the first A will always come this way. Because the detour is 1, 2, 3, 4 links. Okay, if the messages take exactly 1, then the tree will be always this one. Whereas if the messages take at most 1, the messages might take 0. These 2 messages might take 2, but these 3 messages might take 0. So if it's at most, then I can have this path on the tree. You see that? So the at most gives me more possibilities. You see that? If it's exactly 1, then I can just look at the structure of the network and I can kind of tell how the trees can be formed. But if it's at most 1, then if I have 2 paths going to a node, the number of links is not important anymore. If one of them has a huge number of links and the other one has a small number of links, it still might come through the one with the huge number because they might be zeros, okay, in time. You see that? So so these 2 cases are very different. The at most 1 time unit has a lot more possibilities. You see that, right? Intuitively. But we can reason about that a bit. So we're comparing equal to 1 and at most 1 for message delay. Well, if we go from equal to 1 to at most 1, it can only increase. Why is that? Well, every timed execution with exactly 1 is also possible in the at most model, because it's also 1. But the at most model has more possible executions, because messages can be taking 0, okay? So what happens? If you look at so this is a Venn diagram. So here is the set of executions of where all the message delay is exactly 1. Here is a set when it's at most 1. So there's more executions here. It can only be more, because there's more possibilities here. And so the time can only increase. Yeah? Question?
But aren't all the additional possible executions always faster than the ones doing exactly 1?
Yeah, good question. So aren't all the new executions faster? Because in the new executions, we're assuming messages can take 0 time. So you might think, if we add executions where messages are taking 0 time, that they can only be faster. They can never be taking longer.
It's more like because they cannot take more than 1.
Yeah. But I have to tell you, your intuition is wrong. If we allow messages to take 0, so if we allow messages to go faster, the time complexity, the whole system can be slower. That's the point. The whole execution can be slower. And I gave you some intuition here, So if it's exactly 1, then I know that this guy will always be connected in this way, through these 2 nodes. But if it's at most 1, then there exists an execution where the connection will be longer. The chain will be longer. So there are more possible spanning trees. Some of those spanning trees might cause the algorithm to run slower. Okay? So the exercise, and it's not intuitive, I can see, is to find the network, show me a network, it can be a very simple one, where the algorithm will be strictly slower for at most 1, then with equal to 1. Show me and explain to me why. That's the exercise for you guys. Okay? It's interesting, huh? And it's not intuitive, huh? You see, huh? But I give you some hint. So for example, assume now our broadcast algorithm. Assume we let the A messages take 0 or 1, and the B messages are always taking 1. What that means, the A01, is that long paths of A's, they might be fast, okay? But a long path of B's will be very slow. You see what I'm getting to? The tree is actually built through A's. But later, the B's have to travel through that tree that has been built. See what we're saying? So I'm saying, if you allow A's to take 0, then you might have a tree where the B's are going to be a lot slower. You see the idea? Yeah?
So it's not about the building the actual trees, using it afterwards.
Yeah, but the time complexity is both, huh? It's the whole algorithm. It's the building and the using, yeah? Absolutely. Exactly. The time complexity is the total time for the whole algorithm, so the A's and the B's, huh? And the A's are determining what the tree is, but the B's have to travel along that tree. So the B's are not changing the tree, but they have to travel along the tree that has been fixed by the A's, huh? So the question, that's already a big hint, huh? So my question for you is, show me an actual network where the timed execution is strictly higher for at most compared to equal. Strictly higher. That means it's strictly slower. The point is, so this is kind of counterintuitive, the point is that the time complexity is not the time of one execution, huh? It's the maximum over all possible executions. Huh? That changes everything, huh? Yeah?
Is it possible to find a tree like this? Because
oh yes,
yeah,
it is.
because
There's many possibilities.
if we had exactly one time unit, we can just say, okay, no, this one takes 0, and then we are faster.
Notice, but the time complexity is over all possibilities. So as long as there's one very slow one in there, it's slow, because it's the max. See? So there has to be, you have to show me a network where one of the possibilities will be very slow in the at most model. Doesn't have to be all of them. There can be very many fast ones, I don't care. But there has to be a slow one in there, because I'm doing the max. Okay? And I guarantee you it is possible. And you can find that there's many answers to this question. Okay? So that's it. I'm not giving you the answer today. I'm letting you this as an exercise. And you can ask Mathieu about it. So Mathieu has very nicely organized the lab session. First lab session. So this lab session is for you to really understand the concepts, to do exercises. Huh? So it's important to go there. So I try to give you kind of questions during the lecture, but it's not the same as actually doing them in a lab. Huh? So I really encourage you to go to the lab session of Mathieu. Okay? Okay, so I think we can make a small break now. Okay, so now we have already a lot of basics. You know the model, you know causality, we have talked a little bit about complexity. Now let's see how are we going to write the code, the implementation. So I'm going to define for you the way we implement. So throughout a large part of the course, we're going to use a certain kind of pseudocode because it's by far the best way. You can always translate it into whatever you want, Erlang or Java if you really want, if you insist. But this pseudocode it's very well designed and it will make the algorithms very simple because we are going to look at very complex algorithms in this course. So consensus, when you have partially synchronous system, that failure can happen, that is not a simple thing, okay? In the 1990s, that was state-of-the-art research, okay? And research articles were published on that. And we're going to see it in a lecture for now, okay? So you can see it's very important to have the right model, okay? So let me situate a bit what we're going to do. So here's a distributed system. We have some application, whatever you want, big data, Facebook, whatever. You have some kinds of algorithms, which I will call middleware, things like broadcast and consensus. And finally, you have the actual communication channels. So you have the 3 layers. So in this course, we're actually concentrating on this part. Okay? The communication is the network. How the communication happens in the network is not something we do in this course. This is the courses of Olivier Bonaventure. And then there's other courses on applications, okay? Like cloud computing, for example. Huh? Okay. So, these low-level protocols, of course, are not enough. TCP only gives you one-to-one communication, okay? What happens if you have a group of people? What happens if you have a whole bunch of nodes that are working together? It's not enough, okay? You need what we call high-level services, and that's what we're going to see in this course. So here in this yellow and pink boxes, these are the kinds of algorithms we're going to see. Things like reliable broadcast, causal order broadcast. Look at all the different variations. Total order broadcast. Things like shared memory. So very important for the databases. Distributed shared memory is the foundation of all distributed databases. Consensus, also important for databases when you do transactions. Atomic commit is a form of consensus. Group membership, when I have a bunch of nodes working together, but what if one of the nodes fails and it's replaced by another node coming in? So you have a group of nodes, but the group is changing over time. It happens all the time, huh? Nodes fail. So the bank, a bank that is managing your account with a distributed database, maybe it's running on 5 nodes. What if one of those nodes crashes? Well, there's only 4. Well, a new one has to join because you have to maintain the same degree of redundancy. So you have a group of nodes that are working together. And this group can change, but it has to change in a very rigorous and nice way. So you have group protocols. So this kind of stuff, that's what we're going to see. And these algorithms are not so simple, okay? So 2 examples. One very simple example, which we will see in a couple of lectures, is called reliable broadcasts. Okay, let's say I'm broadcasting to many people on the internet and using point-to-point. So I'm sending messages. Well, what can I guarantee? Not so much, huh? What if my node crashes or the network has some problem or whatever? So only part of the nodes will get the message. That's not a very strong guarantee. We want a stronger guarantee. And reliable broadcast gives you a strong guarantee. It guarantees, when I send a message to a group, that there's only 2 possibilities. Either all of them get it, or none of them get it. There's nothing possible in between. All or none. That's a very strong guarantee. Yeah? Very nice. You often want such a guarantee. Yeah? For example, I will give this example, even though it's not politically correct. In a military situation, I'm giving orders to a bunch of soldiers. They should all get the order, okay? All of them. Unless, of course, they are all dead, and then, of course, none of them will get the order, okay? So I need this kind of guarantee, okay? And also, the second one, atomic commit. So here we're talking transactions. So I take money out of the bank, or I transfer money from one account to another. So that's 2 things. Huh? I take money out, and I put money in 2 different places. But the whole thing has to be atomic. That means if there's a crash happening in the middle, the money should not disappear or double or something. Huh? It should be always atomic. Either the money stays in the origin or it moves. Okay? So that's called a transaction. And what happens if a failure can happen at any time? What happens if my system is redundant and distributed? I have multiple copies. All the copies have to move from the old to the new value. All or none. See, it's not so simple, huh? And it has to happen for no matter what kind of failures. Whenever anything can fail, any time, huh? And of course, the failure is always going to happen at the worst time, huh? So, because these systems are doing hundreds or thousands per second. So, a failure is always going to cause things to mess up, unless the algorithm can guarantee that it won't mess up, okay? So this is the kind of stuff we're going to do. Okay, we're going to write the code for these things, and at the end of this course, you will know exactly how to do it, and you'll know how it works. Okay, so in order to write this code, we need a very good language, or pseudocode. And this is the event-based component model that I'm going to present now. With this model, the code will actually be layered. Each layer is adding something and is very simple. So we will have layers, and each layer builds on top of the preceding ones, and each layer has fairly simple code. Most of the code, most of the algorithms, it will be one page of code, and in a big font. It won't be so much complicated code, and it will be easy to see that they're correct. So that's very nice, huh? So that's using the event-based component model. Okay, so how does it work? Okay, so we're going to write code that runs on every single node. And the system is running. So this is our model. At each tick, there's one step. You either have a local computation or you deliver a message, the comp or the deliver. So this is our model, and we're going to write the code for this model. Just to make it very general, there's actually lots of variations of this. In our model, we can, in one step, we receive K messages, so we empty all the in buffs, and we send at most one message to each neighbor, the out buffs. This is the model I showed you, but you can have many other models. There's the model by Rashid Garawi, which is in the book, where you can receive and send one message, or at most receive one and send at most one message to each neighbor. This is the model of Nancy Lynch, okay? All these models are very similar. It doesn't really matter, it changes a little bit the code, okay? So we're going to stick to our model, okay? Okay? So the node executes a program. Each node is going to execute code, and it's not monolithic. It's going to be boxes. So usually I'm going to show it in these yellow boxes, okay, which are like modules, component specifications. So they're like running components, if you want. Each module is a separate thing that's running, okay? So you have kind of like a stack, a software stack. So if I make a picture, the node will kind of run like this. I'll have a module here, and another one, and another one. And these guys are talking to each other, like this. And the lowest one is actually going on the network, and at the top you have some kind of application, okay? So you have a layered structure, and each of these layered things is running one piece of code, single-threaded, okay? And the code is going to be written as rules, what I call rules. And there's a condition upon event. So this means I'm receiving something, and then I run the code. I'm not showing you the code yet. There's code here. And then I can trigger. Trigger means send. Okay? So this notation comes from the book I showed you. So they have sometimes weird notation. So upon event is basically the receive, and trigger is a send. Okay? So I receive a message, I run some code, and I send a message. And this is single threaded. So this is not concurrent. This is running in a single thread. Okay? So that's a single yellow box. Okay? Now what are the messages? Well, again, the messages are by Garoui and Rodriguez and Garoui, they're called events. So these are not compo delivery events. They're basically messages that you send, but not only messages. There's also timers, and there's also Boolean conditions. So I can wait, for example, for some Boolean condition. Or I can wait for a message to arrive, but I can also wait for some set to be empty, okay, a local set. So these upon event conditions can be Boolean conditions of local variables, and they can also be timers. I can wait until there's a timeout, okay? So those are the three kinds of events. And there's two kinds of messages. There's messages going down and messages going up. And this is a funny terminology. This is again Rodriguez and Garoui terminology. These are called requests going down and indications going up. Okay, but let me show you now a picture and give you a better notion of what's going on. So here would be one node running. Each of these yellow boxes is basically a single-threaded computation, okay? It's on thread, and there might be several rules there. So if an event happens, if I send a message here, then something will be running in this yellow box, okay? And each of these boxes is implementing a piece of the system, and there's a layered structure. So if this database component needs to do commit, it will make a request to the commit component, and the commit component does its work, and eventually it sends a result back indication. But the commit component might need reliable broadcast, so it sends a request down to reliable broadcast, and the reliable broadcast will send a return back. Or the commit component might need a consensus, so here we have another component with consensus. So you see, whenever a component needs another one, it sends a request downward. And the answer, there is always a thing going up. And the thing going down is always called a request, and the thing going up is always an indication. So this is the terminology we're going to use, okay? With this, the code becomes very simple. So here in the bottom layer, I have my network component. So here, let's say I have a component called perfect link. This is making reliable computation, like TCP style. Okay, so the reliable broadcast, it might need to communicate. So it's doing a request down, and then the indication comes back up. Okay? So you can see it's a sense of layers. Each of these boxes is running in its own thread. So you can have several threads. So technically the whole node is sequential, but that's actually too strong. In fact, each of the yellow boxes will be sequential. Okay? So I can have several rules in there. So the yellow box might look like this. So let me make a picture just to give you an idea again. So here we have these yellow boxes on top. But let me kind of zoom into one of the yellow boxes so you can see what's inside. Here we have rules. I have upon event, so this is which basically is a receive. Then I write code, and then I have a trigger, which is basically a send. And I can have multiple of these rules upon event, which is a receive. I run code, and I do the trigger, which is essentially just send. And I can have multiple rules like this. So this whole box here is single-threaded, and whenever it receives a message, one of these rules, if the message fits, this one might be waiting for certain kinds of events, one of the rules will be executed sequentially, okay, until it's done. And then the box will wait for the next one, okay? So this whole box is single-threaded. And whenever a message arrives, it executes one rule, okay? So this is a rule. These are rules, okay? So the code we write will be a set of these rules. The rules are basically executed concurrently. There's no order between the rules, but whenever I execute a rule, it's sequential, so I'm only executing one rule at a time, okay? So that's the model. If I do like that, as you will see, the algorithms will be fairly simple, okay? So that's the idea. That gives you a kind of abstract idea, but don't worry, we're going to be writing lots of code in this model, so you're going to see lots and lots of example code, okay? Is that reasonable? Okay, now, we can say there's messages going down and messages going up. So these are levels of abstraction, going down and up. And the ones going down are called request, and the ones going up are called indication. That's important because there's a confusion that's possible. Because this module here can do send. It sends a message which is received below. So a request is actually a combination of a send and a receive going down. Okay? Whereas on the other side, this is the result. So this module has computed the result. It sends the result back upwards. So it does a send. And the module on the top does a receive. So a send and a receive sending information upwards is called an indication. Okay? So you should not confuse request indication with send receive. Okay? Send and receive are more primitive. A send is just sending a message, a receive is receiving. But a request is going down into the stack, and indication is going up to more higher levels on the stack. Okay? So that's how the model is defined. And the actual words that are used come from the book of Garoui and Rodriguez. So a send will be called a trigger. So the code I'm going to give you is very closely following the books I showed you before, Introduction to Reliable Distributed Computing, and those books are highly recommended. And so the model is basically coming from that book. It's basically the first book that has a very rigorous layered structure. It's the first book that presents these algorithms in a simple way where you can actually understand each layer separately. Okay? So they kind of use weird terminology, but I will follow that terminology to be coherent with the book. Okay? So a send, they are calling it trigger. That's the word they use. So they will not use send. This is, in that book, it's called trigger. And receive is called upon event. Okay? So the rule here is doing upon event when it receives, and trigger will do a send. Okay? So that's terminology. That's something you have to basically accept, because this is the terminology used in the book, and it gives us a very simple algorithm. Okay? Now, if we have now a distributed system running on multiple nodes, we will have the same code running on each node. So here we have 3 nodes, P1, P2, P3. Each node has a stack like this, okay? A layered stack with requests going down, indications going up. The very bottommost part, which is called channel here, will have connections between them. So all the network communication happens at the bottom, okay? Only here. This broadcast node will not talk directly to this one. It will only talk indirectly through the channel, okay? If this one wants to send a message to this one, it will basically send it down and it will go up here, okay? That's part of the implementation of this. So these nodes will send messages to each other, but it's always going through the bottom one, okay? So this is how we're going to write the code. So only the bottommost nodes are connected together, okay? Okay, so that's it. That's all. That's the whole model. Not more, but I will start showing you code now for that model, okay? So that's implementation. but there's also specification. Okay? So implementation is what is the code that's running something, but what is that code doing? That is the question that's answered by specification. Okay? So let me explain to you how the specification is running. So there's the interface, which is called the API or the contract. Basically, the messages that it receives and the responses that it gives. There is the properties that it satisfies when it's correct, and there's two kinds, called safety and liveness. Okay? Then there's the model it runs on. So let's say I'm building a broadcast algorithm. Well, does the broadcast algorithm work when there's failures, or doesn't it? Does it work for Byzantine failures, or emission failures, or crash stop failures? Well, those are the failure assumptions. And for each assumption, there might be totally different code. Okay? So telling me what model is it supposed to run on? Also, is it made synchrony? Is my code running on an asynchronous system, or a synchronous system, or a partially synchronous system? The code will be very different, and sometimes even impossible. So consensus will not run on asynchrony with failure, but it will run on partially synchronous with failure. Okay? So small changes in the model can cause the code to be very, very different. Okay? So it's very important to say what model is it running on. Okay? Okay? And then you have, of course, the implementation underneath. So this is what I'm specifying. So basically, what is the API? What properties it satisfies? And what does it run on? This is super important. Small changes in the model can make things, the code, become much, much more complicated, okay? Or even impossible. So that's very important. And then I have the actual implementation. So this is the event-based component model, okay? So let me show you some simple example code. Super, super simple to start, but then I'll show progressively more. So here we have a printing module, okay? Printing module. Okay, so this is a very naive and kind of stupid example. So don't expect this example to be doing incredible amount of sophisticated stuff. So there's the print request going down, and then there's the print confirm message going back up. So this is the request, and this is the indication. It's also called, if it's an acknowledgement, it's also called a confirmation. So this is the interface. I have a single request, a single confirmation or indication. Print request, this is a record. There's a request ID and a string that I want to print. And print confirm tells me that this particular ID has successfully been printed. Okay, this is my printer interface. Okay, fine. Let me show you the code now. So here's the code. This is a rule upon event, like I said, and trigger. What does it do? So it receives print request with a request ID and a string. It prints the string, okay, using some primitive print statement, and then it does a trigger, so it replies saying this request ID has successfully been printed. Okay, this is a very naive and stupid example, but you see what it's doing. The code here is doing upon event PR. It's doing the print, and then it's doing a trigger. PC print confirm. Okay, that's very simple. Let's make it more complicated now. I want to show you an example of a multiple layered system. So this print thing has only one module, but I want to show you an example with multiple layers. So let me define a more sophisticated print called bounded print. Okay? Now the bounded print can only print a certain number of things, and then it doesn't work anymore. So maybe it's only can only print 1,000 things, and then the printer has run out of ink or something. So I request. So this is called a bounded print request now. So it has a new interface. Okay, and I return either okay or not okay. So there could be a non-successful print. And then there's another indication coming up called print alarm, saying if I reach the threshold, it's like a bell ringing, ding-ding, something's wrong, so that it sends another indication up. So basically I can print multiple things until I reach some threshold. There's some number of times, and then after that it will be not okay, and right when I reach the threshold I will get a print alarm. Okay? So how do I implement this? Well, I'm going to build a layered system now, so that it will be implemented like this. So it will use the print as a primitive. So this is the bounded print. Okay? And it will still do print request and print confirm on the lower level one. But this one has other inputs. It has bounded print request as a possible input. It has print status and print alarm as possible return indications. Okay? So this is second layer, and this one is going to use this one as a primitive. So this is just a two-layer system. Thank you. See how I'm doing it? Very simple. It's very simple and naive and stupid, but it's just to show you the layering. So here I have bounded print. Okay? And I can show you now the code of this, which is slightly more complicated. Now there's going to be 3 rules. Okay, first of all, I'm implementing bounded print. I'm using print. So this is a dependency, yeah? So I'm basically using print. So this is print. So bounded print uses print. And now there's 3 rules. Okay? 3 rules, and whenever so there's 3 rules. There's, for example, upon event bounded print request. Then I have some number called bound, a local variable. If it's greater than 0, then I decrement. I do a trigger of print request. You see what it's doing? It's sending the message down to the print module. And if the bound is equal to 0, then it's sending print alarm back up. So as soon as I reach the threshold, it sends print alarm back. Okay? And if you look here, if the bound is equal to 0, if it's not greater than 0, I will immediately send back a print status of not okay. And then I have a third rule here. When I receive print confirm, so print confirm is this thing, coming up. When I receive print confirm, then I will send print status with OK. So this print confirm coming out here will cause a print status OK to be sent here. Okay? And the print status not OK is sent here. And the final thing is, there's also a special event called init, which is only created when the component starts up initially. So there's only one, it's an initialization message. So basically, it causes bound to be assigned to some threshold. Maybe I can print 1,000 things. So predefined threshold is some constant that's telling me how many times I can print before the thing doesn't print anymore. Okay? So this is a bounded printer based on an unbounded printing service. See how it works? It's an example of a 2-layer system. And so this thing is running sequentially. Whenever I receive one of these messages, I will execute one of the rules. While this rule is executing, no other rule can execute. So this thing runs sequentially in a single thread. Okay? It's clear how it's running, this example? This very simple example, we're going to see many, many, many more of these. And real ones for distributed algorithms. Okay, so that's all I want to show now on that. What I do want to show today also is safety and liveness. Okay, so now I showed you how we're going to write the code in this event-based component model with the layers and everything. But what properties does it satisfy? So this is very important. There's two kinds of properties that any system that performs an action to do something will always have correctness, safety, and liveness properties. Okay, always. So maybe you have seen this already somewhere. So who has seen safety and liveness? Some people. Who has not seen it? Many. Okay, so don't worry. So if you've seen it, then this will be somewhat refresher, whatever. So I'm going to give formal definition. I'm going to give you the intuition, because all the distributed systems we're going to be defined will be rigorously implemented to satisfy specification. Okay, so that's very important, because if I change the specification a little bit, the code might change a lot. Okay, clearly. And so it's very important to have a very precise specification. So that's why I'm going to define precisely what safety and liveness is. So first I'll give you some intuition, okay? Safety is, intuitively, bad things will never happen. That's a safety property, okay? So safety property, let's say I'm taking an airplane to Tokyo, for example, the safety property is the airplane will not crash. That's a nice safety property. Okay, it will never crash. And the liveness property is I will eventually be in Tokyo. You see? So that's very easy, right? Liveness says something good will eventually happen. Now, it's very easy to satisfy safety by itself. It's very easy to not be in a crashing airplane. Huh? What's the simplest way to not be in a crashing airplane? Don't take the plane. Huh? Right, exactly. So if I don't step in that plane, I will clearly never be in a crashing plane. Of course, I will not also get to Tokyo. Okay? And something good eventually happened. So it's very easy to satisfy liveness without safety. I can go to any kind of a weird and badly designed airplane, and maybe I get to Tokyo, or maybe I crash and I'm dead. But as long as we're not assuming that it will crash, it's easy, right? It's something good eventually happens. Yeah. Okay. So the difficulty is satisfying both of them together. So that's why the algorithms are hard. Okay. So here's another example. This is a very pragmatic example. This is the correctness of each one of you in this course. So safety means you should never fail the exam, okay? And liveness means you should eventually take the exam. So it's very easy to satisfy one without the other, huh? What's the easiest way to not fail the exam is to do what? Not take it, huh? But you can, of course, if you forget safety, just take the exam. You can always take the exam and fail it and write down random garbage. And then you will satisfy liveness, okay? The trick is always to satisfy both of them. That's always the difficulty. Safety and liveness by themselves is always easy. The trick is when you combine them. So here's another simple example. Traffic lights. Too fast here. Traffic lights at an intersection. So this is not a good example. They're all going to crash. So I have traffic lights at an intersection, this way and this way. So what's the safety property of the traffic lights? What's the safety property?
All lights are red.
Yeah, but you can be smarter, huh? More than one direction should never have green light at the same time. Yeah, all lights are red. That's not letting you be alive, okay? That's not a good safety property because you have no chance of have liveness. But here, you don't want to have a green light in two directions at the same time, okay? That's the safety property. And the liveness property is what? Very easy. every direction should eventually get a green light, okay? So now we get back to your comment. The easiest way to satisfy safety is to just make everything red, okay? If you just do that, then you satisfy safety. But of course, you will never not get anywhere. The easiest way to satisfy liveness is to make all the lights green, okay? Then that's satisfied. But of course, this one is not satisfied. The trick is to satisfy both, okay? So that's always the trick. Safety and liveness, it's always easy to satisfy one, and it's always, you need some insight to do both. Okay. Okay, now a little bit of theory. So I'm not going to give you the proof, but here's a very interesting thing about safety and liveness. Assume we have any property of your system, okay? Any kind of general property, P. So P is any kind of a property that takes the argument of P is an execution, full execution, with all the configurations and everything. And it returns true or false. So that means it's a predicate. It returns true or false. So P of E will be either true or false. Now you can prove formally, if you have this, any property can be expressed as the conjunction of a safety and a liveness property. That means you can give me any property that you can imagine here, and you can express it as a pure safety property conjunction. So, and a pure liveness property. So any property can be split into safety and liveness. So doing safety and liveness is not a limitation, okay? Because any property can be split like that. This is a very famous result of software engineering, which was proved in 1985. It's using topology and kind of abstract mathematics by Alpern and Schneider. And if you're curious, it's very easy to find. So if you're a topologist, if you're a pure mathematician, you can take a look at that. But I'm not going to give you the proof here. Okay? But what I do want to do is define formally what is safety and liveness. I want to be very precise. And in order to do that, I have to define some preliminary concepts. I have to define the prefix of an execution and an extension of a prefix. So the prefix of an execution is the first k configurations, and then I stop. Okay? So an execution, as I told you before, is an infinite sequence of configurations. So a prefix is a finite beginning of an execution. So I have something like this. CK minus 1, etc. Forever. And here I have events. So I'm writing it like this. So the event I write on top of the arrow. So this is an execution. So a prefix will be the beginning, the finite beginning of an execution. So basically the first k configurations, for some number k greater than 0. So basically cutting off the tail, finite beginning. That's a prefix. And an extension of a prefix is any execution. So this is a prefix. Let me call it f. An extension of f, actually it's called p there. P, I don't like p because p is used for property. Okay. And I continue here. I can make extensions. So for example, I end up with ck minus 1, and I can, starting from this configuration, I can start doing things. So I can extend it. And then I can, and this is another execution, okay? This will be another execution. Okay? So the extension of a prefix is any execution that starts with P. Okay? That's reasonable, huh? This is very intuitive, okay? Right. Now we can define safety. Okay? So I start with an informal presentation, and then I give you a formal definition. So basically, it's like this. Every execution that violates safety goes bad, in a sense, okay? It means there is some event in there that is breaking the system, and once the system is broken, it will stay broken, okay? So basically, the example is I'm holding an egg, a raw egg in my hand, I drop the egg, splat. There's no way I can undo that. So all the king's horses and all the king's men could not put Humpty together again. So that's violating safety. So we can then now define that formally. So a property P is safety. Assume I have an execution that violates safety. So the airplane has crashed or something. Then there exists a prefix such that every extension of that prefix also fails that property. So that means when an airplane crashes, there is actually an event there, which is when the airplane has crashed. And no matter what I do after that, that airplane will stay crashed, okay? So there is a prefix such that every possible extension is also failed. Once the system goes bad, it stays bad. So that's the formal definition of safety. So here's an example. Point-to-point message. I'm sending a message from A to B. Okay, so here's the safety property. A message sent is delivered at most once. That's a safety property. Why is it a safety property? Because I can break it. And once it's broken, it's broken. Well, how do I break this? Well, let's say I deliver the message twice. Take an execution where the message is delivered more than once. Well, there is an event which is the second delivery. Okay? And that happens at a finite time. So I cut off the tail after that, and that's my prefix. And no matter how I extend it, it will still have delivered twice. Okay? There exists a prefix such that every extension also violates. So that means that this is a safety property. Once I break it, the system is broken and stays. There's a point at which it's broken and stays broken. Okay, so that's safety. You break it, it stays broken. Okay, basically, that's formally. Let me now explain liveness formally. So liveness is a dual property to safety. So here is a formal definition of liveness. Assume we have an execution that is alive. P of E is true. So this is good, that's living. And what this means is that for every prefix, there exists an extension that is true. That means no matter where I chop the system, I can always make it true. That means my airplane is traveling in the air. And no matter where it is in the air, there's always a path to Tokyo. Always. That's liveness. Okay? There is always a path. You could say, as long as there is life, there is hope. If you want to make a slogan out of it. So here's an example. Again, point-to-point message. The message sent is delivered at least once. Okay? Now that is a liveness property. And we can show that by looking at the formal definition. Take the prefix of any execution. Okay? So there's two possibilities. So maybe there's already a delivery in that prefix. Well, then it's very easy. Any extension, of course, will still satisfy this. But if the prefix does not contain the delivery, well, that's very easy too. You just extend it so that there's a delivery later on. Okay? And if you can do that, then it's live. Then the system is live. Okay? So if the system lets you do that, then it's a living, alive system. You see? If it lets you extend it, so you take any prefix, if you can find an extension that contains a delivery, it's a living system. It's alive. Okay? Interesting, huh? Isn't that interesting? So, personally, so that's the definition. Personally, I'm a very visual-oriented person. I like to think in terms of visual things. So I made a slide where I kind of translate the formal definition into visual metaphors. So here on the top is safety, and here on the bottom is liveness. So I have some execution E. Safety can always be made false in finite time. So that means there exists a prefix. There exists at least one, and the system inside here breaks. What that means is that no matter how I extend it, the property is still false. Terrible, huh? So if I cannot make it true, that means the system is truly broken here. And that means the property is safety. It's a safety property, okay? So there exists a prefix such that all extensions are false. That's a safety property. If I can do that, it's a safety property. And liveness is dual. You can only make it false in infinite time. As long as there's life, there's hope. So here I have an execution. So I can take any prefix for all prefixes. And for any prefix, I can find an execution that makes it true. If I can do that, then the property is life. Then the system is alive and it's a liveness property. Okay? So no matter where I stop here, I can always find a way to make it true. There exists an execution. Not all of them, but there exists an extension that makes it true. And if I can do it, it's a liveness property. It's interesting, huh? But it's very interesting. The two are very different, huh? Safety and liveness. Okay, some intuition more. So there's lots of intuition. And in the algorithms I give in this course, I will very often ask you, I will show you property and I will say, is it safety? Is it liveness? And I expect you to tell me. Yeah? But there's some keywords that happen a lot. And there's some things that you can know. So safety can only be satisfied in infinite time. That means while you're doing the thing, you're never really safe. While you're flying in the air, you're always in danger of crashing up. And you're only really safe after you arrived. So you can never... you can only satisfy at the end. So you're never really safe. And the violation is always finite. So there's always some bad event that happens in finite time when it's violated. And if there's the words never, at most, cannot, these are safety words. Partial correctness is a safety. Okay? That's safety. And liveness is a dual property. It can be satisfied in finite time. So there's some good thing that's supposed to happen. Well, it happens. You arrive in Tokyo, it's good, right? So that has happened in finite time. But you can only violate liveness infinite time. So as long as that airplane is flying around, there's always a chance it might land in Tokyo, okay? And the only way you can be sure it won't is at the very end of the algorithm, okay? And so the words, liveness words are eventually, must, at least. Eventually means some point in the future. So eventually has a very technical meaning. It means in some finite time. Okay? Termination is liveness. Okay? Your algorithm terminates. Okay? Now, some questions for you guys, and that's how I'm going to end today. Here's a question. I have defined safety, okay, to be a predicate, and the argument of that predicate is an execution. So that's my definition. But I can also define it in a different way. So let's say I have an execution like this, with configurations. I can also define it that instead of defining it of an execution, I could also say, I could define a predicate in configurations. And I could define it in a different way. I could say for every configuration, it's true. So it's true for all configurations. So what's the difference? It's for you. I define it for a whole execution, or I can define it for individual configurations. And the safety property is true if it's true for all configurations. Those are two ways to define safety. Okay? I have chosen to define it as a predicate of an execution and not as a predicate of a configuration. Why? What's the difference? Yeah? Why is one way maybe better than the other way? Can you see the difference between these two? That's a question for you. Ah, now we're thinking, huh? Now I want you to think. It's not just accepting. You have to really understand what this means. Okay? So it's not the same to say a predicate is true of every configuration and to say a predicate is true of an execution or of every execution. So it's basically true of all configurations for all executions, for example. And here it's true for all executions. So what's the difference? Is there a difference? Actually, that's not such an easy question because in the 1990s, there were researchers, and there are books from the 1990s that define it this way. So it's not completely true. But in fact, defining it this way is not good. It's much too limiting. The right way to define it as a predicate of execution. Okay? So, maybe I let you think about that. Okay? We'll discuss it next time also. Here's another question, a little bit easier. So I told you in the beginning, an hour ago, that every property can be, that you can take every property and turn it into safety and liveness. Okay? But what about this one? Every message should be delivered exactly one time. So what's going on here? Is that safety or liveness? Every message should be delivered exactly once.
Both.
Sorry?
Both.
Both. Really? It's both safety and liveness.
Safety.
Those?
You're guessing.
At most and at least, so it's a combination of the two we saw before.
You see, you got it. So I actually am tricking you a little bit here. Huh? I never said every property was either safety or liveness, but you can take every property and divide it into a safety and a liveness. So how would you do that for this one? You just said it, I think, okay? So this can be turned into a safety and a liveness. How do you do that? Somebody over there. Or at the back, over here. Yeah?
It should be delivered, and after you have the constraint on the time.
On the time? I don't see the time. You have to do what I showed. I had previous examples with messages, huh? Exactly once. How can you divide that into safety and liveness? It's something and something. What are the two somethings? I actually said it in the previous part of the course. Huh? I used this as an example of message delivery. How do you take this property and divide it into two properties, A and B?
Where
A is pure safety and B is pure liveness.
we have at least one time, it's
Yeah.
safety,
Yes?
and we have at most one time, it's liveness.
Well, it's the opposite. At most
Oh,
once
okay.
is
At
yes,
most
but that's the what you do. So exactly once means at least once and at most once, right? At least once is liveness, because no matter how many times is good, and at most once is safety. So you can so that's how you divide it. You see how it works? You can take any property and divide it into the safety and liveness. Okay? Okay, so let me stop here.